Hi everyone. My name is Praveen, and I am a fifth year PhD student advised by Dr. Vipin Kumar at the University of Minnesota. And I'm with ai-leaf, and I do mostly research in using remote sensing for solving, like using computer science for solving remote sensing tasks. So today we're just going to be exploring one of these such applications of remote sensing, and there are tons. Um, and I think the agenda is we'll start with first what is remote sensing. Then we'll have a bunch of small activities to get you guys in the sense of what exactly we're trying to do and why computer science is necessary here. And then we're going to talk about one of the main tools which we use to solve remote sensing tasks, which is convolutional neural networks. It's a type of deep learning architecture. And then we'll talk about one specific example of an application in remote sensing. And then we'll have time for discussion and questions. Uh, so first of all, what is remote sensing? Uh, Remote sensing, you can think of it is like acquiring information about the Earth's surface without actually like being in physical touch with the surface. It's typically, obtained by taking pictures of the Earth using stuff like aircrafts or drones or satellites. Um, and it's not just observing light. It could be observing anything. Like it could be observing the energy coming out from some specific thing or the heat coming out from a specific place or anything like that. You can think of it like taking the Earth selfie every few days using a variety of cameras. Um, and these cameras can see light or things that even the human eyes cannot see. Um, so remote sensing, in my opinion, is it's a very beautiful thing. It's always amazing for me to see the Earth from the lens that we cannot physically see for ourselves. And on the right, you have some examples of some of these cameras that are used. Like, for example, this is the Sentinel camera, uh, Sentinel satellite. This is the Landsat satellite, and these are some drones that are used for doing this sort of capturing these remote sensing images. Um, so now I'm just going to show you some of my favorite remote sensing images. And you guys can take a guess on what do you think these are? So this is the first one. And you guys can either unmute or get in the chat and you can try to guess. What do you think this is?
Ocean currents?
Ocean current, that's a good guess, right? All right. There are many, so let me, okay, one. Algae, yes, you're right. So this is phytoplankton off the coast of Norway. And these are like algal blooms that do come up every now and then. And there are a bunch of amazing images for this. There are a few off the coast of California as well. And there are some off the coast of New York and New Jersey that are really cool as well. Now here's another one. What do you guys think this is? This is close to home. So, I mean, home in for some of us in Minnesota, but
Is it melting glaciers?
kind of. So this is the freezing of the Lake Superior over the coast of Duluth in Minnesota. So Duluth is here, if any of you have been up there. And this is like in the winter time, it freezes and like this is like the ice melting away kind of. Um, and this one should be easy. This one you guys should be easy to identify. Yep, that's right. So these are the fires over LA that happened in the earlier this year. Um, and you can see that like this is the smoke trail that was captured, and those are clouds and stuff. But um, from these images, you can kind of see that these are like the different types of images that we get to see from these things, and there are a bunch of tasks that we can solve using these remote sensing images. Um, but one thing which you can clearly see from these is that the clarity of each of these images are very different. For example, you can see like this one seems extremely clear, whereas these two seem a little more blurred. That's because there are a bunch of cameras or quote unquote satellites that are going across the Earth, capturing these images every now and then. So this is the list of the most famous satellites that are present across that orbit the Earth every once in a particular amount of days. So Landsat was one of the most famous ones that US started, and it has a resolution of 30 meters and it gives you an image every 16 days. What do I mean by resolution? You can think of it kind of like the resolutions of your TVs. Like, is it a 1080p, 4K, 8K, something like that? You can think of it like that. In the sense, each pixel, how much area on the ground does it correspond to? So if if a satellite has a resolution of 30 meters, that means that each pixel corresponds to 30 meters on the ground. So the smaller this resolution is, the better quality your image would be. And you have the most recent satellite is like one of the most recent one is called Planet, and that has 3 to 5 meters. So that's very, very fine resolution. And there are some satellites that you can pay money for, and like you can tell the company that I want it to be stationed over here for a particular amount of time, and those have resolutions of up to like 30 centimeters and things like that. So you get really, really fine, crisp images. Um, so you can think about the applications of that. Like for example, if someone wants to observe a particular area for some particular reason, um, they can ask that company to station their satellite and observe that area. Uh, so each of these satellites has their own specific use case, which are listed here. But more or less, you depending on the type of activity you're trying to do, you would choose one of these satellites to work with. Um, so for the context of this presentation and what I'm going to explain, most of this is coming from this satellite here, Sentinel-2, and we'll be looking at a few images from there as well. Uh, so yes, remote sensing has tons of applications across various sectors of the environment. Agriculture, land cover mapping, forest monitoring, urban planning, disaster response, carbon control, everything. It has applications everywhere, and there are new applications being discovered every day almost. So um, you guys are in prime time to discover new things. Um, for the context of this presentation, we'll be mainly talking about land cover mapping, and that's mainly what I have been working on for the past few years. But some of the people in my lab and other universities have been working on other things, including stream flow control, lake temperature monitoring, and other tasks that can be solved using remote sensing products. So now before I get into land cover mapping, um, let's do another small activity. Uh, so this is a Sentinel-2 image uh, that is from Minnesota. I think it's from Minnesota, Iowa, somewhere in that region. Uh, and you can see that there are like two fields here, right? This part here is corn, and this part here is soybean. What do you guys think this is? Like this crop growing here is. You guys can use the reactions or chat or anything, whichever one you guys wanna. Okay, I think maybe I'll just get it started. So this is there's no tricks here. Uh, this one is soybean, so this one is also soybean. This one is corn, and this one also is corn. There's no tricks here. I'm not gonna fool you guys. So this is another example. Um, this is soybean. What do you guys think this is?
Can I ask a question?
Yep, sure,
Um,
yeah.
are we just guessing based on like pattern, or are we trying to look at like, because on my screen it just looks uniformly black. I'm not seeing any like gradient or shade behind
Oh,
like the ones that's labeled like soybean or corn. It looks completely the same level of black all the way for all of them. So
right.
I'm just not sure what we're supposed to be like keying into.
Yeah, so I think yeah, maybe if you I couldn't get but what I'm trying to show why this is this. Yes, we are trying to look at patterns. For example, like this color and this color look very similar. And if you do look at what they are, these are both soybean fields. But you can see that this color is slightly different from this color, but they're both corn. So this is what I'm trying to show. And I'll show you just another example here, I guess. This one will make it, hopefully this image is a little more clear. So this field here is a cotton field, and this field here is a soybean field. What do you think this field is?
Do we know when these pictures were taken? Like which time of year?
These are all like July. You can think of it
Ah,
like July.
I
Soybean,
think it's soybean.
soybean. So this was a trick. This is actually a cornfield. So the reasoning is because the way that these satellites capture these images, if you look at just these three channels, which we are looking at, RGB, they may look the exact same. But if you look at the other channels of light that they're looking at, it would look completely different. Um, so here's another one where we have this is a soybean field and this is the rice field. What do you think this one is? Yeah, so you would think it's rice, but the trick is again this is soybean. Uh, and now again, this is because of the growth patterns of these crops. They vary, and sometimes in different time scales they look the same. Um, but this image is from July. If you look at the image from August of this exact same field, you can see that now they look the same. Like this place and this place look more or less the same, and you can see that it's starting to distinguish from this um, rice field here. Uh, so basically, what I'm trying to get at is that our eyes can only do so much. We can't we can't identify all of these by ourselves, and we need some other special sort of tool or some sort of algorithm which can do this for us, or which can reading these images better compared to what our eyes can see. And that is what convolutional neural networks are. These are just one of the few deep learning models that have been used for doing image analysis. Um, and they basically learn how to analyze or these images that you pass. So most of the material that I'm going to show is taken from this Medium article, which I've cited down here. It's a good article. You guys should take a look at what they do. Um, but effectively, a CNN it has been inspired by the visual cortex, and it has a bunch of neural network layers, which are basically mathematical operations. You can think of it like that. Um, and they come up with a particular output. And the output is what we are interested in. And we are trying to make this CNN learn a specific task or something. So if you look at an image is effectively a collection of a number of pixels. If you were to look at just this image here, you won't be able to make out anything about where this image is coming from. But if you get a little more context, like if you look at a little larger area and then even a larger area, oh, you'll know that this pixel is coming from the eye of an eagle or something like that. So this, as humans, we do this automatically, where we have this hierarchical representation of an image, which our brain processes quite straightforward. But the computer doesn't know that. So the number one thing is, first we have to see how does the image, how does a computer read this image? So a computer just sees this as a bunch of numbers. Each of these pixels can be represented on a scale from 0 to 225, or if you're looking at satellite imagery, it goes from 0 to like 3000. But effectively, all of these are just numbers. And what we want this computer to do, or this CNN to do, is to take this set of numbers and give us a particular output, that this is something, or this is that thing. Um, so we're going to just see in the next few slides how CNNs take this set of numbers and then just give us an output on what we want to see. So let's say our task was we want to identify which digit is being shown here. So you can take this image, split it into these numbers, like get the numbers of this, create like a single long array of 784 dimension with all of these numbers, and then pass these through a set of mathematical operations. You pass them through a set of mathematical operations, there are various choices for these mathematical operations, but there's a standard few that everyone uses. And you can read more about this in that article. But effectively, you would have a bunch of, you can think of it like this node, for example, takes whatever number is here, multiplies it by 5 and divides it by 3 or something. And then that gets here. And then there's another operation here. And then after that, you have at the end, you get a value for each of these nodes at the end, which correspond to the output that you want. So let's say that the mathematical operation after all of this node ends up to be like 0.1. This one ends up to be like 0.4, but then this one ends up to be 0.8. So this is like the highest. So you would choose that to be your output for this for this input image. So this is just the, generally how most of these neural networks work, is that they try to predict numbers for all the classes of interest that you have, and then you take the one with the maximum probability or maximum value. So a typical CNN has a bunch of mathematical operations. These are just the names of these operations and what they effectively do. But effectively, you can think of it like, you can just think of it like a multiplication on that number followed by some division or clipping or something like that. But you have the convolutional layers, the activation layers, the pooling layers, and then fully connected layers, which combines everything for final classification. So this is like just a caricature of what you do. You have the input, which takes it, does some math on it, does some scaling on it, and then gives you an output. And this, based on this output, you determine what the output of your algorithm is. So this is how it would work for images, like multi-dimensional images, like RGB images, like what we're working at. It would take this input, look at this set of pixels here to create a smaller one here, and then this would like keep on happening over and over again till you reach what we saw 2 slides ago, where you reach that smaller dimensional vector, and then that smaller dimensional vector is again acted upon by a bunch of layers to get the various outputs that you have. You might ask, what happens if there's a new class here that we want to add, because it's, when this model is trained, it's only trained with the specific outputs that you are training it for. But let's say you want to add one thing here, you have to train a whole new one. So that's the whole problem with this whole approach, which is what current research people are trying to solve. Now to get a little bit into the math of how this happens. So we saw in the previous that it is like kind of taking a chunk and then like creating smaller numbers for it. So that's what this is kind of doing here. You define like a 3x3 kernel. You act on each of these pixels to create like a new output. So you start with this image, and then using this kernel, you create a new image entirely. And you keep on doing this over and over again till it reaches the certain spot that you want it to reach. And the thing is, these kernels themselves change. Depending on what this kernel is, you learn new features about the input image. So that's where the innovation in this was, is that um, if if you define a set of like a 10 kernels, each kernel's output image would correspond to something else, and the concatenation of all of those would be a whole new image in itself. And maybe that image, it would be easier for us to distinguish what that image is. So that was the whole innovation here. This is just a slide on the math behind it. Like, if this is your input image, you have this as your kernel. You can use this mathematical operation to get this smaller output. And you can do this again and again and make it smaller and smaller till you reach a point where, okay, now I can just distinguish which class this image is. So, like, for example, if this was your final image, you could say that if this number is highest, it's a dog. If this number is highest, it's a cat. If this number is highest, it's a horse, or something like that. And that's how these machine learning algorithms work. And there's a lot of math involved, and this is very math heavy, and how these things backpropagate and how these things evolve over time. And that article does go into all of this. So it's a good read. So this is the entire layout. You can think of it there's an input image, goes through a bunch of things to make it smaller. Then you get a vector array, which consists of all the information, the best information, you can think of it, from this input image. Then it goes through a bunch of more mathematical operations to get a value for each class of interest that you have, and then it just chooses the best one as the output. So this is how we can use computer science to get from an image to a particular output. And this was all in the image domain. So, and satellite images are also images, but the task that we'll be trying to solve is a little different. Here, you're just taking this entire image and you're trying to just get a single value for the entire image. But in land cover mapping, which is what we're going to talk about soon, you'd want a value for each pixel. So CNNs have a variety of applications in many different domains. Mainly, you have applications in computer vision and natural language processing, but they also have applications in object detection, segmentation, classification, counting, and everything. One of the most famous CNNs ever has been the UNet, which is an algorithm that was created for doing pixel-wise classification. And you would have seen units being used in most of the autonomous driving stuff that's being used now, or even medical imagery, everything. Like even cancer detection still uses UNet to the best of my knowledge, right? Even now, because it's more reliable compared to the other methods that are being created now. But effectively, you can see that this is your input image, and using these CNNs and using all of this math, you can get like a pixel-wise output as to what class each pixel belongs to. Similarly, here, this is in the driving context. You can see that this is your input image, and you would just assign a single value to each pixel that you see, so that this one is a car, or this one is a pedestrian, or stuff like that. Over time, people have tried to make these CNNs much faster, because if you're doing autonomous driving, you can't wait for like even a second. You would want the results instantaneously. So there are a lot of variations on this and how to make it faster. Um, I think YOLO is the fastest, or I'm not sure actually, but yeah, that's what CNNs and UNets are. But effectively, what we saw is that something that can take an image and it can give you an output for that image, better than what our human eyes can do. That's what we saw. And now we're just going to apply this in land cover mapping. So land cover mapping is basically figuring out what's going on the ground. That's the easy layman way to put it. Is just like you're just trying to figure out what's going on the ground, using images, using satellite images. Most of these try to tackle environmental issues. So we require timely information on land use and uncover to make sure that we are on track with a lot of things. One of some of these include like conversion of forest to farmland, loss of cropland due to urbanization, degradation of soil, and all of these things. For example, even if you look at the satellite imagery across of Minneapolis over time, like if you see it like 20, 30 years ago, you'd see that the city is very small. You'd actually see that St. Paul is distinct from Minneapolis. And then over time, you can see that like the urbanization has increased, and you can see that these two cities have become one. Um, so yeah, what are the challenges that we typically face while doing land cover mapping is there are many a times we can't assume that we get crystal clear images all the time, because we did see that these images are taken once in like 5 days. So let's say we are looking at some region, and on the day the image is taken, there's like a bunch of clouds. And your goal is to try to map what is going on this field here. You can't do much. Like the cloud is blocking it. You can't do much. Similarly, sometimes the sensor malfunctions or something, and you just get like half image. So if you're trying to map a field which is here, can't do much. Um, and there are sometimes you get images that are like useless in terms of information. For example, this is an image in Minnesota. This is the Mississippi River going here. Uh, and you can see that if your goal is to try to identify what crop is growing on, this is an image from January. It's completely snow. There's no point of using this image to do crop mapping. And similarly here, this is an image in November, before the snowfall hit. And there's no information here. Like all the crops are dead. So what are you going to do? Ideally, you would want images that are like cloud free, in the growing season, and like don't have enough information for you to distinguish what crop is growing. But then again, we did see in the previous slides that even if you have one such image like this, you still won't be able to make sure what's going on, because each these images may look very similar to us via our eyes. So that's why we need some sort of time series analysis in this. Um, for example, if you look at each of these crops and you look at how green they are across the year, you can see that each of them have a different greening cycle, a different time when they green up and when they green off. You can see that alfalfa stays green pretty much throughout the year, whereas cotton and corn, they have like this dip. They go up and down relative to the others. Almonds and oranges are both trees, so they stay similarly green almost throughout the year. Whereas grasslands die out in the winter when you can see that there's a drop in the greenery there. So this shows that not only we need an account on space, because we saw that CNNs take into account the neighborhood of what they're doing, but we also need some time component in it. So we designed an algorithm which takes into account both this space and time, and we called it STAT, spatiotemporal attention. That's what we call it. Um, um, but yeah, it's a CNN-based method which uses both space and time to give a particular output. Uh, Now, to test our methodology, we chose to look at a region in California. This is the California crop belt, which consists of 11 tiles. A tile is basically a region which the Sentinel satellite goes across US and takes multiple chunks of images. When it takes one image, the area which is covered is called a tile. So the entire California crop belt can be covered in 11 Sentinel tiles. And this region is responsible for a lot of the crops that we get throughout US. Like some of the tomatoes that you get in Minnesota are actually coming from here. So this is a very crucial region for mapping and very important for uh, livelihood in general. Um, so that's what we aim to basically map this area using satellite imagery and try to come up with better labels as opposed to what the government gives, because actually the government does give out labels for the entire USA, but they make a lot of mistakes. So we try to develop a method which takes in satellite imagery and tries to give a better output for these particular regions. Um, and this is like the split that we used in terms of which regions we used for training and which regions we used for testing. Um, and this was some of the outputs that we got. So I'll just talk a little bit about this. This row here is what the government gave, and this is what we got as our output. And you can see that this is the image in July. So you can see that like this is almonds, and like this is I think hay, winter wheat or something. Uh, but there's nothing growing here. You can see that nothing is growing here. So like this is definitely wrong. For example, here's another one. The government has said that there's nothing growing here, whereas we said that there's a cotton patch growing here, and clearly in July there is something green there. So this shows that our methodology has helped in improving these classification results better. You can see some other similar cases here where we have more smoother, more correct output compared to the others. Uh, and we released this entire thing as a data set called CalCrop 21, which is available publicly, and you can take a look at it. But yeah, this is basically an application of using CNNs in remote sensing, because this methodology STAT uses convolutional neural networks. So it used the satellite images input, used the CNNs as a methodology, as a remote sensing tool, you can call it, to try to get the output for this image. And this is just one of the applications that are there in remote sensing. So with that, I think we'd just like to conclude on this. So first, we explored what remote sensing is, and then we had a small activity to depict the limitations that of our eyes. Like, our eyes can only do so much. And then we explored what CNNs were, as they are a way to go beyond and understand images better than what our eyes can process. And then we saw how CNNs are applied in land cover mapping. And we saw that using these satellite images and the amounts of data for training, we can get better results than what is considered the gold standard at this point. And with that, I'd like to thank everyone for listening and happy Halloween. And I'm open to any questions if you guys have any.